Thank you everyone for attending this session. Today I will be talking about crafting your cryptographic library from scratch. I'm Mamy Hatsimbazafi. I worked as the ZK engineering lead at Tyco. So just a quick technical presentation of Tyco. It's a type 1 ZK VM. We don't change anything from Ethereum, no hashes, state trees, transaction trees. It's exactly the same as the yellow paper specifications. We might just change like the maximum gas limit at the moment while we are optimizing the VM. It's also a base rollup, so the consensus is driven by L1 validators, and so it's the same decentralization as on Ethereum, permissionless and deterministic block execution. Who am I and why am I talking about cryptographic library? So I used to be a Ethereum core dev on the Nimbus client at Status. In particular, I contributed to the IETF standardization of hashing to elliptic curve and BLS signatures. IETF standardized TLS v1.3, for example, so it's a very big standards body. I also contributed to the completeness of all the Ethereum consensus cryptographic test suites. And I implemented as well all the Ethereum consensus cryptographic protocols, including up to EIP 4844. That will be very relevant for all ZK and optimistic rollups. And today I'm the ZK engineering lead at Tyco, working primarily on accelerating ZK primitives. So we have three ways to accelerate them: number theoretical acceleration, high performance computing style, so using CPU caches, memory bandwidth parallelism, and hardware acceleration. And today we have a long course, seems like I have 46 slides, but many of those are just one line. So before I go over the agenda, I want to talk about what the main goal of the talk. It's to resolve the unknowns. So turns out the more you know, the more you realize you don't know. And the less you know, you have this paradox called the Dunning-Kruger effect. It's the less expertise you have, the more you think you know. So this talk is about giving you signposts for your journey into cryptography engineering and keywords to search for. Things like constant time, for example, things like threat models that you need to be aware of to make a good implementation of cryptographic research. And also, I want to talk a bit about psychology, because this is a field where I think everyone needs to deal with imposter syndrome, because you open a paper and you have so many math symbols that you don't understand, and then you're like, did I choose the right career? Maybe I should just play a mobile game or something. So those are the three main things I want everyone to be more aware of after this talk. Agenda. Well, at first, I'll go over my journey into cryptography. I'm not a cryptographer by degree. I'm not a mathematician either. I'm a mechanical engineer. So I didn't really do much maths related to prime numbers, for example. I did do linear algebra, but that helped maybe for lattices, not for elliptic curve or pairings or polynomial commitment or zero knowledge proofs. Then I'll go over the meaning of don't roll your own crypto. I assume that's one of the first results you had when you research how to implement a cryptographic library. I think this is important to address. Then some points about how to prepare for your journey into writing a cryptographic library. So what can cryptography do? I think you did some of this on Monday. I talked about threat models as examples, so I'll talk about this at this point. Then mapping the journey of implementing cryptography. actually implementing it, and then like community psychology. Well, you are in a great community, the Phoenix project. So I guess first point, it's solved, but you have to also showcase your work. I think it's important to stay motivated and continue, and then learn how to receive critics, and not last, last but not least, receiving critics from cryptographers, because cryptographers tend to meet a lot of what is called crackpot cryptography. People that thinks they did unbreakable cipher or schemes, and then they become grumpy old men, I guess. So I'll address that as well. Okay, so now onto my 5-year journey into cryptography. I started to work on the Ethereum blockchain in 2018. And into cryptography almost right away. Why? Because I started to work on Nimbus, the Nimbus client, which was written in a language called Nim that I assume almost no one knows. There are many reasons why Nim was chosen. Syntax is similar to Python, so it's very easy to convert Ethereum spec, which were in Python, into Nim. It has types. It's compiled to C, C++ very fast. And it's also very easy to wrap C or C++ code with no cost. So this was chosen to write the Nimbus client for a client optimized for mobile devices. But it had no production grade big integer, no networking, no cryptography. So everything that you need for an Ethereum client, so peer-to-peer networking, cryptography, it was not there. So we had to do everything from scratch. The good thing about that is that when auditors came to audit codes, they were like, oh, you control everything from the bottom up. So there is no supply chain attacks, which were very rampant in 2020, 2021 on JavaScript and Python repositories. So in 2018, that was kind of my first contact with cryptography. I had, well, two related tasks. One was providing a big integer. At first, I wrapped the C++ big integers, but they caused issues. So I implemented big integers from scratch. And other task would be implementing SecP256K1. I took a week to explore the problem space. I failed to implement it. Well, not that I failed, but after a week, I decided that it would take way too much time to do this. And we had a product to ship. So instead, we wrapped the Bitcoin libsecp256K1 library. What's the takeaway of this? Sometimes you need to implement things from scratch. Sometimes you need to wrap production grade libraries. Well, check your use cases, the timeline, and well, it's basically a decision, a product decision. Fast forwards 2 years later, now working on the Ethereum consensus layer, what was called Ethereum 2. We introduced new cryptography there, the BLS signatures on BLS 12381 curve. This was used because they were very efficient because they could be aggregated. And unfortunately, there was nothing except, I think it was the Chia blockchain that started to use them ahead of many others. And then others joined, like Algorand, Filecoin, Ethereum, Tezos, and others. And there was a kind of a consortium of 6 blockchains that tried to push forward for standardization or at the IETF. On my side, I saw all the elliptic curve backend as a black box, the pairing backends as a black box, because this was something, well, I failed to implement for ACDSA at the time, but the higher level protocol were easier, and I just use ready to use libraries for those. Then I went through security audits, first time doing security audits, and also cryptographic security audits, learned a lot. It's very helpful to understand what kind of vulnerabilities. And I guess that's also one of the reasons I feel legitimate to present something about crafting your own cryptographic library here before you, because I actually went the whole way until security audits. Then I also did some multi-threading for batch verification of BLS signatures, things that go a bit over the Ethereum spec, but which is necessary for reaching high performance on hardware like Raspberry Pi. So since 2020, I kind of got the bug of cryptography, and I restarted this project that I did for a week to try to implement cryptography from scratch, but as a personal project, renamed it to something to Constantine, which is a play with the name Constant Time. Constant time, which we'll see later, is something necessary for security when you use private keys. Currently, it's the fastest library for BLS signatures, including BLAST, BLST. I've added full implementation of EIP 4844 2 weeks ago, which is also called proto-dank sharding. It's either top 1 or top 2 with GNARC on performance. Single-threaded is the fastest. Multi-threaded, it depends on the number of cores. I couldn't optimize for more than 18 cores. So while the GNARC team optimized for up to 96, so I don't know how it's performed there. It's being fuzzed, sponsored by the Ethereum Foundation, and part of Google Crypto Fuzz, which fuzz all open source cryptographic libraries. The Ethereum Foundation Fellowship Program is sponsoring vertical trees to be implemented in Constantine for the L1, the execution layer. Okay, so enough about me. But what you can take away from this is it's a long journey, 5 years from me, even 2 years to get started to do something really interesting. And you are likely starting in, just a month. So don't worry if it takes a lot of time to master. It's a hard topic, but it's very rewarding. And I guarantee that many rollups, many blockchain teams are looking for people that have development skills and cryptographic skills as well. So if you're here also because you want to find a job, it takes a lot of it takes time, but there is a lot of opportunities out of this. Okay, so part 2, the meaning of don't roll your own crypto. There is something called Schneider's law from Bruce Schneider, who's one of the most influential cryptographers out there. There are many ways to of how this law was formulated. Schneider's law is from 1996 or something. Anyone from the most clueless amateur to the best cryptographer can create an algorithm that he himself can't break. And there are even formulations from the 1864, I think, from Charles Babbage, who kind of one of the first programmers, let's say. And I think it's the third one. Few false ideas have more firmly gripped the minds of so many intelligent men than the one that if they just tried, they could invent a cipher that no one could break. There is kind of a parallel in software engineering. It's that the if you're very clever, you write something that is so complex that you need twice the time to maintain it or debug it. So it's easy to do something that you cannot understand, but maybe someone has tools to break it. For example, the most famous cipher of all time is called Kaiser cipher from the Roman Empire. And they just moved the, it's a substitution cipher. So instead of A, you encode using O, which is the 15 letters, and you move all encoding by 15. But this is easily defeatable by frequency cryptanalysis. So you just look at the frequency of all the text, and you match that with the frequency of how letters are used in a language, and you decrypt this. And there are many other ways for cryptanalysis, which is a science of decrypting those things. So don't roll your own crypto is not about preventing you from implementing standards. It's about preventing you from coming up with novel ways to be broken. So if you implement standards, you're okay. If you come with novel ways and you think it cannot be broken, you're very likely wrong, unless you've been doing this for 10 years and you've broken other people's stuff. So unfortunately, I guess, despite being a scientific domain, you have this argument of authority for don't roll your own crypto, because you have the burden of proof is on the side of the one creating his own crypto. It's also about, so you can learn by rolling your own crypto. You have to, otherwise in 10 years, there won't be any more cryptography engineers out there. But don't trust yourself in production. You need to have tests. You need to have fuzzing. You need to have auditors. You may need to have formally verified implementations. But do everything you can to learn, but don't trust yourself in production. In blockchain space, we have so many issues already with like Solidity smart contracts. You can see when reading rec.news. Yeah, don't add the cryptographic issues also. And regarding auditors, they are fully booked for 3 to 6 months. So if you plan to launch a rollup soon, well, it's time to book your audits. So don't roll your own crypto also applies to seasoned cryptographers. 3 months ago, there was this paper called Revisiting the Nova Proof System on a Cycle of Curves. So Nova is something that got very, very popular since 2021. It's a technique called folding, which significantly optimize proof system. And for further optimizations, the implementation of Nova, which was described, formally described and also reviewed for normal elliptic curves, it was changed to a 2-cycle of elliptic curves. I won't go into the detail of what a 2-cycle curve is. You can search on the announced of the pasta curves by Zcash, but it helped for efficiency a lot. But this seemingly small change was not secure. There was a soundness vulnerability. Fortunately, it was just, I think, a couple of lines of code to fix this. But it means that even cryptographers, while they are deep into other things, in this case, optimizations, they can forget. And they are rolling their own crypto. And then there are, I guess, more YOLO crypto things. So there is this storage company called Mega that had several issues in the past 18 months with, I think, 2 or 3 papers for attacks against Mega. So basically, they added a lot of building blocks to try to secure their things. But then one of those building blocks became an oracle. So an oracle is something that can give you one bit of information, just yes and no. And you can use this oracle to break and retrieve a secret key. So the most famous example is something called the padding oracle. If you look for padding oracle, you'll find a lot of, I think, likely a Wikipedia page. But Mega had added the oracle by mistake, and then also error codes were not properly designed, and they allowed attacks that could retrieve RSA public key. So the very first paper was in 2022, and you had to use 512 logins to be able to retrieve the private key on Mega. And after a year of improvement, you only need to log in twice to break Mega. So the thing is, in cryptography, once you have a small vulnerability, it opens the way for further and further and more complex attacks that ultimately can completely break your system. This also happened for something called isogeny-based cryptography in last year for the post-quantum cryptography competition, where someone pulled out mathematics that were unused for 20 years, broke a post-quantum encryption scheme, not encryption, but authentication scheme. And it took at first days, and then it was reduced to minutes on a laptop. So if something is broken, you cannot add more and more and hope to fix things. You have to deeply review what is broken, because otherwise people will start mounting more and more complex attacks. And in minutes, you'll be completely wrecked. Last thing about the big warning. So we're really in red alert, the red alert section, and then it will be more optimistic, I reassure you. There are lots of things that are design bugs. So if you look at this, this is a TCP connection state machine. So how you open a network connection. This one is unencrypted, but when you add encryption, it becomes TLS, and it becomes really, really complex. So it's very easy when you code this to forget to put a transition between sent and closed, for example, or listen to close. And when you forget this transition, your program ends up in a state where you don't know what's happening, and you might have buffer overflow, you might retrieve, hijack the session of someone else, you don't know. And when you have this, there is no programming language current. Actually, there is, but there is no common programming languages, even if they have borrow checking, even if they have a functional with monads, or that prevents you from this. So the way to prevent this is called formal verification. This is something that is growing, but you need to be aware that there is a class of bugs that cannot be checked by compilers. That's the bugs that are in your mind. So I said that there are some programming languages that actually can do this. There is one that's called Ada Sparks. There are others, like everything that is used for hardware, like VHDL, can also provide formal verification. Why in hardware it's important? Because when you create, for example, a chip, let's say you transfer data from memory to a cache, and then from L2 cache to L1 cache. if you have a bug and your a bit is flipped, maybe you crash the program or make it do wrong result, and that's you need to have 100% insurance that does not happen. For regular programs, this is very useful. For example, when you do two-phase commit protocol for databases or for distributed computing. This two-phase commit protocol is something similar to the hotel and train problem. Let's say you want to book a hotel and you want to book a train to go to Istanbul for DevConnect. Either you book both or you don't want any. So you have something where you have this commit and rollback, and you need to make sure that there is no state where you can book the train without the hotel or the hotel without the train. Another way it's used is critical sections without locks. So it's during multi-threading when you have two threads that want to write to the same parts of the code, and you need to make sure that they write one after the others. Otherwise, you'll have something called torn reads or torn writes, where one thread starts to write, I don't know, 10, and the other start to write 12. Well, maybe 22, and you end up with 12 because one puts a 1 and the other puts a 2. And this 12 never happened, so you have a big bug. Another more sorry issue is as a ferrac radiotherapy machine. So this was something that was used in the 80s. It killed at least 6 people because what was happening is that when the machine was adjusting and rotating, if at that point you pushed on the enter button, it ended up in a state that was not programmed, and it created a lethal dose of radiation, and so many were killed. And it took 2 years to reproduce the problem. 2 years of tests, and it happened. They reproduced by error, by mistake, because someone pressed the button. Like they were trying to do all the steps that were written in the procedure document, but actually someone wanted to speed up things and press the enter button, and that was the mistake, and that was not taken into account in the design of the machine, and it killed people. Which is why in the aerospace industry and medical industry, this is critical to have formal verification, and it's starting to grow in cryptography. So after this, we have what's called managing expectation, because we have so many potential issues. It's important to not misrepresent or omit from your README that your code is experimental, unaudited, may launch missiles or eat puppies. Yeah, very important. Now, we read all the warning signs, and if something goes wrong, you cannot sue me, okay? Before your journey, let's do a recap of what cryptography can do. So there are 5 building blocks, I'd say, that cryptography can do. First one is authentication, ensuring that you communicate with the right person. You do this with digital signatures. Second is integrity. A received message has not been tampered with, so you want to verify that. You use hash functions. You have confidentiality, so only the intended recipient can read a message. For this, you use encryption with a cipher. You have then 2 other goals that are mutually exclusive. One is non-repudiation. You want to prove that a sender sent a message. And the other is plausible deniability. You want to leave reasonable doubt that an action was not taken. So I'll give an example of non-repudiation. In the past, you had cable companies and you had people doing recording what was on the cable. So they might use cryptography for traitor tracing and proving that someone recorded without without any doubt. And plausible deniability is of course needed for privacy reasons. So you want to leave doubt whether you send $100 or not, and for what what services or goods you got in exchange. Continuing, one of the first things you need to think of when you do your cryptographic library is thinking about your threat models. So this is something that is also used in cybersecurity. In many engineering disciplines, you can assume goodwill. People, like when you build a house, they want something that lasts because it's good publicity. And no one is going there to destroy your house when you're not there. With cryptography, that's not the case. Everyone wants you. You have to assume that people will destroy your house if they can. So usually in cryptography, you have Alice and Bob, who are the people that want to establish a secure connection, want to talk to each other, want to verify that they are who they claim to be. Then we have the other personas, Eve, the eavesdroppers, and Mallory, which is a malicious party. And you need to think of what kind of attacks you want to defend against, from who. Like, are they local in your company? So is it an internal attacker? Is it someone from the outside? Is it NSA? Do they have billions to break your scheme? Maybe you don't try to protect against those. Yeah, and so this means well, in cryptography there are three kinds of security, I'd say. One is information theoretic security. So this is something that is provided, for example, by hash functions, by many ciphers. It means that there is no way to break this. There is computational security. So this is mostly used for asymmetric cryptography, cryptography that relies on a trapdoor function. So a function that is easy to compute one way, but very hard to compute the other way. There is usually a problem, a mathematical problem that protects the breakage. Usually it's a discrete log problem for RSA, the elliptic curve discrete log problem for elliptic curves. The issue with this is quantum security, for example, is a way to completely change how computations are done and to break computationally secure algorithm. And then the weakest security is crypto-economic security. This was, I think, the main invention by blockchains, crypto-economic security, which is, okay, instead of making it theoretically impossible or computationally impossible, I'll just make this economically impossible, because if it takes you 10 billions to break this, actually, it's not worth it for you. But in cryptography, we usually deal with information and computational security. In blockchain, we deal with crypto-economic security because it enables more efficient scheme, well, at the price of security. Now, when you create your own crypto library, there is something that has been more and more popular in the past decade. It's called misuse resistance. So internally, you want your library likely to be very flexible, very modular, because cryptography moves fast. Well, yeah, it moves fast now. I think 10 to 15 years ago, it was moving more slowly, but in the ZK space, it moves very fast. But the actual interface, the API for the users, you want them to be misuse resistant because it's very easy to shoot yourself in the foot and leak secrets everywhere. So this is an example of what not to do. OpenSSL is a very, I think, the most used library, a cryptographic library of the world, but it has many options and many guns you can shoot yourself with. So this is an illustration of this. The other thing is something called side channel attacks and constant time. So, oh, I have the slide in double. I'll use this one. There are many ways to break cryptography, but there are theoretical ways and there are actual, when you implement theory, you are confronted with reality. And in reality, you can measure things, and we can measure timing, you can measure power usage, you can measure electromagnetic emissions. So all of those, if you look at the very lower level of what a secret key is, a private key, it's a sequences of 0 and 1. And all public key cryptography, if you implement them naively, when you do a 0 for RSA, for example, you double your result, and when you have a 1 in your secret key, you double, and then you add again the input. And so by analyzing timing or the power usage or electromagnetic emissions, you can find the sequence of 0 and 1 in a secret key. And this happened for WPA3, the new Wi-Fi standards for trusted platform modules. Even Intel SGX, the secure enclave, was broken by a thermometer because they had a thermometer on the CPU, and you could read the variation of temperatures to read a secret key within the secure enclave. Happened for many TLS / SSL implementations for libgcrypt and GPG, and even for Twitter. So ad companies could retrieve what was the Twitter username of someone that visits their website by testing the time it takes to answer to load some profiles on Twitter using cookies, Twitter cookies. And last but not least, picking your programming language. So
sure. Yeah, sure. You can list this.
I'll mute everyone. Yeah.
So in when you pick your programming language, so before doing cryptography, I did AI, data science, and I tried to implement a Go playing bot because I'm a Go player, and I've been looking into computer Go for a while. I tried to implement a Go playing bot in Rust. What happened was I had to learn Rust, borrow checking new concepts at the same time as learning AI concepts, and it was too much. And after finishing like my first baseline, my first prototype, I just said, okay, I'm stopping this. This is too complex. So first, start with something you're comfortable with or that is easy to learn, because cryptography is a big problem. It's a big domain space. And then even if you start, so the second part is if you implement low-level cryptography, so something like finite fields, elliptic curves, SHA-256, Blake 2, you will need at one point precise control over memory and assembly for security. So assembly is not used only for performance, it's also used for security because compilers can defeat non-assembly and make those non-constant time. So if you look into, this link, the github.com with constant time arithmetics, you have examples and papers about compilers doing the wrong thing for cryptography. But even if you start with Python, for example, which is fairly easy to learn, when you re-implement this on low level, Rust, NIM, maybe C, C++, Go, Ada, for example, it's not lost because you can use it to write test vectors and to compare results. It's less likely that you have a bug in two different implementations than in a single one, except if you do one-on-one copy. But as you get more experience, you will find out issues and you re-implement them better. So now that we have all the prerequisites, the warnings, how to approach things, what do you need to implement? I think the best way is to start using cryptography first. You pick a program or library. Don't pick OpenSSL or pick a very well-documented part. Otherwise, you'll be dispirited, I guess. Find what works, what doesn't. Take notes on what you use. Frame it in terms of, like, if you think about authentication, confidentiality, etc., you'll find out that there are it's always the same. Authentication is like sign, verify. When you do confidentiality, it's encrypt, decrypt. When you do integrity, it's hash and equal, compare. So when you do something more complex, maybe polynomial commitment, it's setup, commit, prove, verify. The good thing about cryptography is, even if it's complex, the actual API are really easy. And once you see patterns, that will help you create a mind map of what you should do at the end. I've separated implementation into two kinds of cryptography, the non-algebraic one. The non-algebraic one has no mathematics. So it's everything that is ciphers, hashes, message authentication code, key derivation function, random number generators. You have an official spec coming from NIST or from the IETF, and you have official test vectors, follow them, and use differential fuzzing or testing against a reference implementation. So things like OpenSSL, libsodium, and other things. When I say no math, it's for the implementers, because some ciphers or message authentication code, so for example, AES, uses binary arithmetic. But you actually don't care about this because they detail all the operation and you can just see this as a black box. For message authentication code, I'm thinking about poly 1305, which is actually 2 to the power of 130 minus 5. Internally, it uses polynomials, but you don't care. You just follow the spec, and it's very easy to do. Now, what matters most in ZK? Algebraic cryptography. Lots of maths. You'll see finite fields, you'll see groups. Maybe if you dive, you really want to be algebraic geek, you'll see monoid, and other abelian groups and other fun stuff. So this is used for something called public key cryptography, which uses a trapdoor functions, something that is easy to compute and hard to inverse. It's a case of modular exponentiation for RSA, scalar multiplication for elliptic curve, pairings for pairing-based cryptography. Everything is based on this. And for lattices, it's shortest vector problem, if I remember correctly. I put lattices in a different separately because first of all, it's not used in ZK at the moment, but it's used in fully homomorphic encryption. And I never implemented them yet. So now ideally you've been a user of cryptography, so you know at the top level what you want to offer. So let's say you want to offer BLS signatures, which uses pairing. You know that you want a sign and a verify at the end. And then, so you have a top view, and then you have to build things bottom up. Finite fields first, elliptic curves, and then pairings. You don't have to be generic for all type of finite fields, all type of elliptic curves from the get-go. It's relatively easy to refactor in most programming language to be generic, but try a concrete implementation that you can test as you go. Don't chase too much things at once. And now, let's say you have your elliptic curve library or maybe even polynomial commitment, and there is a new math paper that comes out, or a new spec, and wow, so many math, and you deal with imposter syndrome. You're lost and you're doubting. So the way I do this is, first of all, I read the abstract and overview of the goal of the paper. That's very important. Sometimes we jump into the fray and we forget to read the most important thing. Is it a paper about performance? Is the paper about a new scheme and everything? And if you want to, like, once you've done that, you can model this paper as a black box. So the function first, forget about all the equations that are inside. Math doesn't bite, though it might give you headaches. And often there is an implementation that you can test with. You can also email the author on the ZK space. You go on the Zero Knowledge Podcast FM Telegram group. You ask if someone has an implementation, or maybe the author are there. And then you prototype. I think that's the best way to start with and be practical. It also, I forgot to put this in slides, but I think it's important to know your learning style. So some people are theory before practice, and they want to see things demonstrated with proofs. And then once they are convinced, they start to implement. Often it's more the researchers that are like this. And then there are those that need to see the code and need to practice before, so more bottom up, before understanding what's going on. And those are usually more the engineers. So find also your learning style so that you start with something that doesn't discourage you, because that's the worst thing, doing something where you feel it's draining. Now, on to writing your own implementation. Well, README, I mentioned this before, do the disclaimer about missiles and puppies. Once your repo becomes a bit more mature, create a security disclosure process. What kind of mail address do you provide a PGP key so that it's encrypted and only you or only a security team can decrypt the message? Because if your library is used by a lot of things, let's say you create a wallet, you don't want this to be in the world. And on the security disclosure process, make sure that the experience of white hat hackers is good. Now I will be talking about a tool called SageMath. So SageMath is a distribution. It's Python, but modified to work with everything scientific. So it's used for number theory, math, cryptography a lot, but it also can do stuff in matrices, for example. But the very good thing about SageMath is that creating an elliptic curve takes 2 lines of code. So P is my prime number. I create GF is a Galois field, so a finite field. And then I create G1, which is an elliptic curve with parameters. So elliptic curves are usually y square equal x cube plus ax plus b. In the case of pairing curves that are used for ZK snarks and SecP256K1, a is always 0. So it takes a line to create that curve. And then I wanted to test scalar multiplication. So scalar multiplication is for signing with your secret key. And it's also to derive your public key from your secret key. So it's a very important operations, and it's a huge bottleneck in cryptography. And you just need to do Q equal scalar multiplied by P, and then I just dump that into a JSON, and I have my test vectors for my real programming language. So I use this for prototyping protocols implementations. I use this for debugging because, as I said, if you have a different implementations and there it's even done by someone else, it's hard to have a bug. It's way less likely to have a bug there and in your own code. I use this for generating constants because I don't want to type hexadecimal inputs all the time. And I use this to generate test vectors. And now following up on testing. So obviously test vectors are really good, but my experience is that, well, when in regular cryptographic libraries, finding tests was actually quite hard, which is why I resorted to SageMath to create my own. And the other ways to test are something called property-based testing. So with algebraic cryptography, you have a lot of properties that you can use. For example, you know that multiplication is distributive over addition. So A multiplied by, in parentheses, B plus C is equal to A multiplied by B plus A multiplied by C. And this is a test that you can do. And if you made something wrong in addition or multiplication, it's likely that you will fail. Other tests, you can do same thing for exponentiations. There are similar structures from pairings. You can test that multiplying by the neutral element, so 1, you get the same result. That adding 0, you get the same result. That adding the opposite, you get the neutral element. Yeah, so plus the neutral element on the elliptic curve is a bit special. So yeah, many tests that you can do this way. Fuzzing, there are many kinds of fuzzing, but basically it's crafting inputs that tends to create edge cases and make your program crash. So the highest level of fuzzing, I'd say, is using either AFL, American Fuzzy Loop, or Leap Fuzzer. And those, they use something called genetic algorithms. So yeah, genetic algorithms. So it's they use crossbreeding, and they monitor your applications to see all the branches that exist in your application, and they try to take them all and crash your input, your program with input that you didn't think about. And for this, the genetic algorithm is literally picking mutations and randomly doing them, guided by the if then else's in your code. I've linked something called a poor man's fuzzer that I use. Why do I use this? Well, when you do low-level cryptography, constant time, there are no branches. So it's an issue because now the fuzzer cannot find the branches that help guide them into corner cases. So my poor man fuzzers is something that I've reused from Bitcoin's SEC-P256K1 crypto library. It's something that tends to create lots of 0 or lots of 1 in a row in any numbers. The reason why is that those tend to create carries or borrows when you do additions, or overflows when you do anything else. And that's where bugs are hidden. And they found a bug in OpenSSL in 2015, I think, using this. At first, they thought they were buggy, but actually it was OpenSSL that had a carry bug that had 2 to the power of minus 64 chance of being triggered. And the last thing is differential fuzzing. So this is when you use 2 different implementations and you run them both under the fuzzer and you check all the differences. If you implement your code as constant time, it can be interesting to differential fuzz with a non-constant time implementation, because this way, that non-constant time implementations has branches. This is also relevant if you actually implement cryptography in zero-knowledge circuits like Circom, Halo2, Cairo, Noir, all those good stuff, because in a circuit, you don't have branches as well. So you might want to differential fuzz between a circuit and a normal implementation. And last is benchmarking. So especially with ZK, cryptography is often a bottleneck when you connect to Cloudflare, for example, to retrieve internet pages from a cache. When you connect to a website, most of the time is establishing the crypto connection, encrypting things, decrypting things. And then, well, it depends on how image heavy is the website. Like if it's Netflix, obviously it's the video. But if it's Google, let's say, you spend a lot of time doing cryptography. So what to benchmark? You have time to benchmark. This is useful for comparing between CPUs. And throughput, which is nice. It's a different way to represent things, and it's usually more relevant in my experience. Cycles, it's something that is excellent when you're optimizing, but you cannot use it to compare between computers, because cycle, if you use turbo, it's wrong. If you yeah, because basically your clock is at, let's say, on my computer, the clock is at 4 gigahertz, but it can turbo to 5. So the cycle count might be off by 20%. So it's only useful if you compare, optimize on your own PC. But on your own PC, it's very useful. And if you want to compare across libraries, I think you need to use cloud instances. Amazon has very well-defined cloud instances, and this way you also make sure that there is no parasites from I don't know, your mouse, your Zoom call, VS Code, your browser, and things like this. But even then, when you do benchmarks, try to do 1,000 or 10,000s of iterations, something that takes at least a millisecond, and you divide by the number of iterations you did. Many languages have something built in. Go has their Go bench. Rust has Criterion. Haskell has Criterion as well. Yeah, many languages have something built in. And last part, community. So writing cryptography, writing complex code can feel like a very alone, thankless task, and something where you feel like no one understands what you're going through. Every time you open one of those fancy proof system math paper called Nova, Supernova, Hypernova, Protostar, Protogalaxy, Sonic, Supersonic, they all think you're crazy. So find a good community. There are a couple that are with 100 to thousands of people. If that community doesn't have a section, ask for something for show your work, because that's how you spur discussion. You get more people interested. Maybe you get a new contributor. Soon there will be Hacktoberfest in 4 days. That might be an excellent way to get people into helping you. And then you have, I guess, the critics. Recently, I was involved in some drama between Starks and Snarks, because, well, there was some drama following Eli Ben-Sasson from Starkware doing a talk comparing Starks and Snarks speed, and then it came back to, oh, you're measuring the wrong thing. You cannot compare. It's apples to oranges. Usually in the blockchain space, you have many people that have lots of goodwill. And as long as you stay humble, it's when you start making tough claims or you threaten the livelihood of people that it can get tricky. But like as a new joiner, if you say my code is experimental, I'm looking for feedback, I'm new, stay humble. Normally, you should get good critique. Otherwise, it's someone that's likely toxic. If you misrepresent things, you might get critics from cryptographers. And there are some that are, if you search for a crackpot cryptography, you'll see some examples even on the IETF mailing list for standardization, people thinking they have new protocols and getting shut down really hard. It's the first time it will not be personal, because they are solicited left and right by people thinking they found something groundbreaking. But yeah, it can be a bit abrupt. So if you want to receive critics, start with your community. Hopefully there is more senior ZK cryptographic engineer in there. And that's it. It was an hour and 5-10 minutes or so. I'm finishing with a cryptographer joke. So cryptography is the art of transforming a security problem into a key management problem. So yeah, that's what happened with blockchains. How do you store your seed? So yeah. And if you have questions, feel free to ask. I'm Mamy Bazafi. You have my GitHub, you have my Twitter, and I'm the lead at Taiko.
Thank you, Mamy. This was very interesting. And a few folks in the comments have also asked for the PDF of the slides. So once once you share it with us, we'll share it with the community as well.
I removed some typos. I think community was written community, and so within like today.
Sure, no problem. There were a few questions, but I think they were answered. One was, what is the difference between a prover and a proposer? So there was already an answer to that question. And then an example for formal verification. That was my question. Like, how do you sort of like what entitles a formal verification for a language or for a piece of code? Like, how do we contextualize?
Okay, so there are two ways to do formal verifications. One is ugly for mathematicians, and one is elegant. The ugly one is, let's say you want to play tic-tac-toe, and you want to prove that you solve it. You can show that all this from your move, any answer has a proper one, and from this you can prove that you beat someone, whatever they do. This is brute force. This is also called model checking. So let's see if I can share. So the first part is called model checking. It's about verifying that all the states are correct, are expected.
Are you sharing a browser screen? Because I still see your slides.
Oh. So model checking is you want to make sure that everything is checked. So this is all the states are correct, and there is a correct transitions for everything. This is used for checking multi-threading, like concurrent data structures, for example. This has been used by 12 bits, so an auditor, for checking the Ethereum consensus. You can read this formal analysis of the Casper consensus algorithm with TLA+. I've used it personally for my own multi-threading runtime to ensure that there is no bug in my queuing algorithm. And so this is the ugly one. It's like using a bazooka and trying to check everything. And the let's say elegant one is something that is used for example, something called fiat crypto. It's called correct by construction cryptography, and if you look into the proof, for example, let's see, you actually have a mathematical theorem. So you have a proof system, an assistant, it's called usually COC, and at one point it say, oh, I cannot deduce the next step so that this is equal. And at that point, you need to provide a proof that that the two lines are correct. The transitions is correct. And this way you have basically something that you know is correct from the very scratch. And so Fiat Crypto is a very nice repo that can generate C code, Go code, Rust code, Zig code from for elliptic curves. And there is something similar for TLS, which is called HACL star. Let's see if I search Project Everest, which was sponsored by Microsoft, the INRIA in France, to provide TLS 1.3 formally verified from the bottom up.
Okay.
And you have some explanation of verified software. So it goes beyond just memory safety. So this is something that Rust provides. You have no design bug, no bug at all, basically.
Okay. I'll check out these resources. Thank you, Mamy. There were 3 more questions. One is, do you have any links for folks to join the Taiko dev community?
Yes. So if you go on the top right, you have a Discord, and you can see that it's discord.gg/TaikoXYZ.
Okay, perfect.
You can see at the bottom of the screen.
Okay, perfect. So we will share this over the email as well if this is interesting for folks. Then there is a question about EIP 4844.
Yeah.
It's just, how does it work?
Huh. Let's see. I think there were some documents. Yes, there is a website called eip4844.com with some link. If you learn through YouTube, there is a video with Vitalik and Denkrad and Proto. So Proto Denk sharding is from Proto Lambda, Denkrad, and the sharding design from Vitalik. So you have everyone there, plus Tim Bako, who's community lead at Ethereum. Optimism is very, very invested into 4844, so they also did a deep dive. And you have spec, but also, I guess, high-level explanations. The goal is we create a new type of data that Ethereum consensus and execution layer can store. And this data is managed by rollup. It's 4 rollups, so that they have more space without using the... So in blockchain, what's the most costly is storage, because data is stored forever. And so those blob carry data at a lower cost.
Okay, perfect. I think the links are very helpful. I have also shared that over here. I'll share the video as well once I'm able to find that. One last question is, yeah, Saurabh requested for the YouTube video. I think it's there on the, okay, it's here. All right, awesome. One last question is, any community for cryptographers that you can recommend?
So I've seen for cryptographers, so not implementers, but cryptographers, there is a Zero Knowledge Podcast FM Telegram group. So I think if you go over ZK Podcast, this one, and at the bottom, you'll have a Telegram group there. So there is no short link for the Telegram, but if you go at the bottom, you'll have the Telegram. There are 2,000, over, I think 2,300 people there. For implementers, you can find some of those in ZK Hack community. So it's also something that zereknowledge.fm is doing. Is there a link to ZK Hack? Doesn't seem so. There is also...
I think it says join the conversation, community.zkhack.dev.
Yeah, so there is ZK Hack. There is Lambda Works, Lambda class. Let's see, lambdaclass.com. So they are building a cryptographic library from scratch. In Cairo, I think. Yeah, I think that's already a good start.
Yep, they are building the Cairo VM Rust version. So yeah, and I think some more stuff as well. Okay, I don't think there are any other questions. All right, okay, folks joining now, but we are just closing the session. Can all these links be shared with the slides? Yes, we'll share all the links. I've also shared on the on the group. There's a when mainnet question for Taiko. I will leave it up to your discretion if you want to answer this or not. But
yeah, I can answer for now. It's targeted for Q1 2024. The only unknown, I guess, is when 4844, because after 4844, all rollups that are on mainnet will have to have a hard fork. So let's say we release and 1 month later there is 4844. It's bad for people because they need to hard fork right away.
all right. Thank you so much, Mamy. This was a very interesting session. And thank you everyone who was able to join. As we mentioned, after every session, there's going to be a very small homework. So for this session, I just like pick the homework on the go, which is if you can write a small blog or a Twitter thread about SSL. So OpenSSL is the one that's basically the open source cryptographic library, and you can write whatever you want about it, but just for people to understand what OpenSSL is, you can talk about SSL, TLS, and you can go as deep as you want or just keep it as short as you want. And that's your small homework. As we told you, every session will have small homework. The coding sessions will have probably a larger homework to submit a piece of code and stuff like that. We are going to have CIRCOM sessions coming up. We are going to have how to build a small ZK dApp using CIRCOM and different protocol sessions coming up. So every session will have a small piece of homework. And as you keep completing it, you'll be able to collect an NFT at the end of the ZK month series. I'm sure you all have a lot of funky NFTs. This is just like a small, nice, like participation NFT that, you know, you did all the steps, and we just want to thank you for this. And yeah, so as we'll send you more details over email, you have to use 2 hashtags, ZK month and ZK with TPG for your Twitter. And then if you have the Medium article, do send it over to us as well. And I encourage everyone to do this exercise because this will only strengthen your learning process throughout this entire month. And yeah, this was our ending week. This is our last session of this week for the cryptography week. Next week, we start with Introduction to Zero Knowledge Proofs. That's on Monday. And going forward, we'll keep informing you of the upcoming sessions as well. Yeah, you can reach out to Mamy. He shared his Twitter. And if you have any other questions as well, he's available to answer in case you decide to go deeper into cryptography. Don't forget to credit him for this amazing lecture. Thank you so much, Mamy. Thanks for your time. We really
Thanks.
appreciate it. And we hope that folks got to learn like a bunch of really cool stuff from this session. And if there are any questions, we will send them your way over TG.
Thanks.
Thanks, everyone.
Goodbye.
Have a good one. Yeah. Bye.